So, good morning, everybody. Welcome to the workshop on geometric complexity theory. It's my pleasure to introduce Avi Widgerson from the Institute for Advanced Study. I think he doesn't need any introduction. He's so well known. He will speak about matrix rank, applications, open problems, whatever. Please, the stage is yours.
So I realized after listening to talks here for 2 days that this talk is going to be quite a bit different than many of the talks you heard. It's first of all, it's not so directly connected to the topic discussed here, GCT. Although some of the things I'll mention are definitely related. It's more just taking advantage of the fact that there are so many algebraists and algebraic geometers in the audience, and that I have so many problems that are on the border of algebra and combinatorics, that are some or most are motivated by computational complexity, that it's an opportunity. Maybe you can help us solve some of them. All these problems, so this talk, another difference will be that it will have about 7 or 8 topics. So, I'll switch contexts many times. The common theme will be rank, and it will be about, this will be the theme, and then we'll see lots of variations on rank and questions about these variations. So, if you lose me on one, you can wake up for the other, and it's a brand new. Right, so let me start. So I'll start the basic notion of matrix rank, which needs no introduction. So I'll have a field, and for most problems I'll mention the field wouldn't matter. I mean, the open problems are open for any field. Maybe you can do it for some. And we'll work with n by n matrices, so over this field. And the type of, for each topic, it will be more or less the same structure. I'll tell you a measure, like rank, and I'll tell you that, well, let's say here, if we take a matrix here, matrix A, then we know that, I mean, it's trivial, but let me just say it, for most such A, the rank of A, let's say, is bigger than n over 10. Right. Even bigger. I will be sloppy with constant, they will not matter much. So one type of fact will be that most objects have high complexity measure. And then the task, the really difficult problem, which was mentioned here many times, is the randomization problem, is to find, so exhibit an explicit A with high complexity measure. In this case, rank. Well, this is a trivial problem. We know many problems. For example, if I take the identity matrix, so that's, in this particular case, it's easy. As you'll see in all the other cases, it's not easy. But this is the type of, this will be the structure. And when I say exhibit and explicit, so we discussed there are many arguments here about the notion of explicit. First of all, I don't think that there is such a large difference between mathematical explicitness and computational explicitness, because most things you will come up with that you think are explicit will probably satisfy both the mathematicians and the computer scientists. What complexity theory allows you to do is to give a formal definition of what explicit is. What explicit is, why is this an answer, an explicit answer? Because really the sequence, IN, all these matrices, they have, for n in n, they all have rank n. So it's a sequence that's easily generatable. What does it mean? Or explicit, what does it mean? It means that, in general, what we would like to do is to have an algorithm that runs in polynomial time in n that will generate A sub n in this sequence. That's what explicit would mean formally. So for example, IN is clearly easy. We don't necessarily need that the sequence will exist for all integers. For example, a matrix that will come up a lot is what's called the Adamar or Sylvester matrix. It's just an orthogonal plus minus 1 matrix. Okay. Orthogonal plus minus 1 matrix, we don't have it exactly for all integers. We know many integers for which it exists. For example, yeah, for example, yeah. But anyway, we know it's very easy to generate such matrices, let's say, Hn, where n is the power of 2. Right? This is basically the Fourier transform matrix of gf2 to the n, the gf2 to the k. So this will be good enough. That's explicit. Okay, so let me go to the first, and please stop me with questions if anything is not clear. So let's go to the first non-trivial complexity measure, and this is the topic is matrix rigidity. One thing you'll see is that many of these problems are motivated from many different fields in complexity theory and theoretical computer science. So somehow, lots of things boil down to rank-related issues. So I'll tell you where these problems are coming from in all cases. So what's matrix rigidity? We say that the matrix A is RS rigid. First in words, a matrix is rigid if not only it has high rank, but also all its neighbors in the Hamming distance have high rank. If you change few of the entries, it remains high rank, no matter how you change these entries. So it's if for every B, so that B minus A in the Hamming distance is at most S. So this means just that we have Bij different than Aij for at most S such Ij. Okay. So if you change some of the entries, S of the entries, the rank of B is still at least R. Okay. And it's really easy to see over any field. Sometimes the word most has to be clarified when you work over, I don't know, infinite fields. But basically, most A are very rigid. Even if you change like 10% of the entries, you cannot reduce the rank below linear. It's a simple counting argument or dimension argument. So most A's are rigid. How about getting explicit examples like this, where the best we can do, so explicit, if we want explicit, what we do know is that, for example, the matrix H, this H sub n, the Hadamard matrices, there are non-trivial bounds. I mean, they are not difficult, but R n squared over R. And it's more or less the best we can do. So notice that here the product of R and S is cubic, and here the product of R and S is quadratic. And what we really want is explicit examples that beat this quadratic bound. It would be, so an open problem is explicit A's, which are RS rigid. RS, let's say, bigger than n to the 2 plus epsilon. It's a great challenge. People worked on it for decades, and let me tell you why they work on it for decades. Different type of parameters here will imply different things. This problem was introduced, the rigidity notion was introduced by Valiant, who showed that if you can get something like n over 10 n to the 1 plus epsilon, so one example of this trade-off, explicit rigid matrices. This implies, I'm not going to specify, but it implies some circuit lower bounds. Boolean circuit lower bounds. This will be a major. We don't know how to do this kind of thing. And Razborov showed in a different regime. So this is an implication to cell complexity. There is an implication to communication complexity. If you can get some like n to the epsilon, here n squared over 10. So you change 10% of the entries, and all you want is that the rank doesn't drop below n to the epsilon. It looks like it's trivial. We don't know how to do this. And this will imply certain communication complexity lower bounds for those who know. Doesn't matter what they are. But anyway, it will be important. It's a big open problem, and we don't know how to solve it. So that's the motivation.
What did you write there?
Yes, I said it doesn't matter. It doesn't matter. There is some communication. Here, there's.
Yeah, but
Yeah. No, I mean I can
what is
give
that letter? P,
pH.
P, H.
And this is P space. It's just complexity classes, but not in the Boolean functions, but for communication complexity. We'll separate two complexity classes that we don't know how to separate, like P versus NP in the communication. Okay, questions about this? Yeah.
So in the code, but you don't know how to construct explicit rigid matrices, like before in the last seminar. But the problem there was with it was like squares of prime.
Yeah, so notice what I meant explicit. This is a very good question. You want a polynomial time algorithm, right? Square roots of primes, not squares of prime. You want a polynomial time algorithm that will write down this matrix. In particular, the output should be matrix of integers of, let's say, polynomial bit length, right?
Why integers?
Well, whatever an algorithm can write, it can write bits, it takes bits, yeah. So I don't allow you to cheat and put here, transcendental numbers or square root of primes, which you need really, for the result to hold, you need infinite precision, stuff like that. Yeah. Yeah.
So that variant series are explicit means what? In polynomial time?
Yeah. Yeah. If you can generate such matrices in polynomial time, then you find a problem in P, in fact. You will have a problem in P which has a sort of superlinear circuit lower bound.
Superlinear.
It's not quite, I'm not specifying, but non-trivial, something we cannot reach. Yeah.
So sorry, but so what if it was just sort of some linear combination of primes or polynomials and primes? Is that explicit?
Yeah, sure. I mean, as long as there is an algorithm that writes them down. Okay. Of course it is, yeah. Yeah, you can write primes, you can.
You can really think a computer program.
But in fact, Joseph, let me go back to what I said in the beginning. It's also okay if you just describe to me something with roots of unities like the Fourier transform matrix over other groups, something that you can define for me for all n, right? I'll be happy.
But you do want it to have sort of, square roots of primes, but not do.
Yeah, okay, yeah, infinite precision is a problem.
You want to be able to do arithmetic.
Yeah. Well, it's a great discussion actually about explicit, but forget the definition. Give me a sequence of matrices, and then we'll argue. When Klim says square root of primes, I'll tell you that's not kosher because it's infinite precision.
Why don't random matrices count?
Well, I mean, we know that random matrices count. They are fine. I don't want random. I want you to deterministically generate this. This is the problem. The whole problem, like I said, is a de-randomization problem. We would know that random matrices are good. We would know that in all these cases, and we would not know. Okay.
So for example,
By the way, let me just tell you one of my favorite, this is something that was invented by Howard Karloff. The problem of, you have a space, and most objects of the space have a property. Right? This is the situation here, and you want to exhibit one. This is the problem of finding hay in a haystack. It turns out that finding hay in haystacks is not an easy problem. I mean, there are many examples where it's really difficult.
But it's even more proving that you took hay.
Yeah. Sometimes it's hard to certify.
It's hard to prove that.
Yeah, certify. Yeah, that's right. Okay.
Well, even in many cases, I mean, so in algebraic geometry, there's this basic object called the moduli space of curves. And you can talk about curves with special properties or general curves. general curves are dense, and nobody knows how to write one down once you get past a certain genus. And it was developing the theory of this for a long time.
So mathematics is full of examples like this, and this talk is just about examples that have to do with variations on rank. So, okay, good. Let me switch to a different example. I want to talk about approximate rank. You'll see that there are various twists. Approximate rank, and here I need the field to have some distance metric on it, so it can be R or C. Anyway, so what's the epsilon rank of a matrix? It's very similar to rigidity. You are allowed to perturb the matrix, but now you are allowed to perturb it only in the small perturbation in L infinity matrix, in L infinity distance. So the minimum rank, the rank of B, is that B minus A in L infinity. And this is a friendlier problem, much friendlier than the rigidity problem. Excuse me?
You have an upper bound of the entries of A?
No.
Epsilon is...
Well, yeah, you can normalize. You can think of A as a, let's say that it's a plus minus 1. That's it, the matrix plus minus 1. Okay. So of course, it's really easy to see that most A, if epsilon is small, let's say epsilon is a small. Most A, rank epsilon of A is linear. This is easy. And it turns out that here exhibiting a particular high complexity A is not very difficult. Our friend, the Hadamard matrix, is like that. So it turns out that also.
It's worth mentioning that here most of them with Epsilons are actually full rank.
Yeah, but as I said, I don't want to go into this is true. I want to be sloppy. In many cases, there are sharper estimates. In almost all of them. For the Hadamard matrix, it turns out that you can very easily prove it's just an eigenvalue calculation. It's very close to N. So it's really easy to prove the bound, but sometimes that's not the interesting example. So let me ask you, instead of the Hadamard matrix, what do you think is the rank, the epsilon rank of the identity matrix? You're allowed to perturb the entries up to epsilon, and you want to reduce the rank as much as possible. How far can you reduce it?
1.
1? No. Is it big or small? I'll tell you. It's an easy result. Turns out that it's very small. And this is one way to think about it, and one motivation to study this epsilon rank of the identity matrix is this Gilbert-Varshamov bound in coding theory. And this is the motivation for studying it. And here the question is, okay, this is easy to prove by a probabilistic argument, and the main question here is make this upper bound explicit. So we know that such matrices exist. Low-rank matrices which epsilon approximate the identity, we know they exist. And this is also Johnson-Lindell-Strauss dimension reduction. So it comes from. So here explicit construction of epsilon approximation is a fundamental problem in coding theory. It's about rank. And another fundamental question in coding theory is what's the right answer? That's just an upper bound. There's a beautiful lower bound by Noga Alon, which is almost tight, log n over epsilon squared, log 1 over epsilon. And distinguishing the two is about the most basic question in coding theory, the rate versus distance. So we don't know. Yeah.
So we know things about, coding theory and JL and things. I mean, what are the explicit upper bounds for this question?
What are the explicit upper bounds? So for example, if you put here a square, log n squared over epsilon squared, this we can do explicitly. Or if you do log n over epsilon cubed, this we can do explicitly. Yeah, but we are far from, it's very basic. Okay, let me switch again, and now I want to talk about sign rank. Another basic problem. It comes from both computational learning theory and communication complexity, and there are other motivations. I'm not going to get into them, but let me define it. Here we will look at matrices that are just plus minus one matrices. And we need to be over the reals, because we need signs. Reals, rationals, doesn't matter. Okay, so what's the problem here? What's the sign rank of a matrix A? It's the smallest rank you can have of a matrix that has the same signs in every entry like A. So A is a sign matrix. You can change the numbers any way you like, maintaining the sign. And the question, how low can you get? So the minimum rank, so that Bij times Aij. Okay, so, if you've never seen it, it looks weird, but actually it's important. And here also it's true that for most A, the sign rank is linear. Close to n right now. Anyway, and again, you want an explicit one, and the best we know. Okay, let me first point out, this is unlike almost all the statements like most A blah 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 I'll make, all of the others are really easy to prove. This is not easy, or it's rather easy once you know some real algebraic geometry. It uses
So you mean most in terms of the number of ordinance or something?
No, I said most.
Yeah, most A, so
A is a sign matrix, yeah, finite, yeah. And it uses the Warren theorem. Basically, the bound on connect components that hypersurfaces can cut up space to. But anyway, if you know this basic result, then it is easy. And you are looking for explicit examples, and we don't know anything linear. I'll tell you the best we know. This is a result of Forster. And he proved that the sign rank, the Adam-Ard matrix, you see there is only one example. The biggest problem with explicit examples is that we know very few families of matrices or of objects. It's either those or random. So this at least square root n. Actually proved a better theorem, more general theorem. The sign rank of any matrix A, any sign matrix A, is at least n over the spectral norm. Okay, and that, of course, follows. And basic open problem here is find A with linear explicit A, sign rank. It would be extremely interesting for these applications I mentioned. Okay, let me see how I'm doing. Let me tell you about one more. Actually, maybe I'll get to it at the end if I have time. So let me just mention another thing I wanted to talk about is rather than looking at the rank of matrices with the same pattern of sign as a given matrix, you can ask about the same patterns of zeros versus non-zeros. This you can do for any field. And it's really interesting. It's related to rigidity, but maybe I'll do it at the end, or if you ask me.
So are there any known relationships between these questions and
Some, yeah. So here is
between these and things like, I don't know, other standard things in combinatorics, Ramsey?
Yeah. So there are some of them are more on the wishful thinking side than on the. I mean, they are related. So, like I said, in the applications, you can see where they are related to. You know, margin complexity in learning theory is related to this. Between these three, there is no direct relation. But if we were going to talk about this zero non-zero pattern instead of sign patterns, then at least in my mind, there is a project we've been pursuing with the FV, with Shubangi Saraf, how it might give explicit. So let me just state a theorem. I will not motivate it, but I'll just which related to this, that has to do with the zero non-zero rank, but I'll just make it explicit. And so there are connections, and there are connections to other things like Ramsey and extractors, and which I'm not getting into. Let me just on this zero non-zero rank. So it turns out that everybody, here's another explicit example that people like of matrices, is the projective plane matrix. So if this is N, so projective plane matrix. The projective plane matrix, I have noted, it's the incidence, matrix of lines versus points in the projective plane. So it has roughly, square root n ones in every row, and every 2 rows have just one intersection. That's how it looks. So it turns.
You're speaking to this audience, you should say the finite projective.
The finite projective plane, but it's not clear that n is would have taken me a long time to draw an infinite matrix. Yeah, finite projective plane. N has to have some particular size, but it's not really important. In fact, what I'm going to say, so we can call it P, what I'm going to say will be true for any matrix which has a constant times square root n. So an arbitrary constant times square root n ones per row, and a constant number of common ones for every 2 rows. So something like this. So what I'm going to say is true for any such matrix P. What is the statement? The statement is that the rank, so the zero, non-zero rank of this matrix. So what does it mean? Any matrix that has the same zero non-zero pattern of this guy has linear rank. So think about it. It doesn't matter how you, let's say, over the is or over some. In an arbitrary, crazy fashion, you make these ones into big and small and transcendental numbers, whatever you like. You cannot make the rank drop.
So the number of ones is at least square root of n per row?
At least and at most.
I see, okay, it's exactly...
Well, it's between root n over 100 and 100 root n. Yeah, so that's, and this, in my mind, very related. It's a part of a project of maybe building rigid matrices. What it says is that if, for example, you change entries, right? What is rigidity about? Rigidity, you are allowed to change entries arbitrarily, right? And you want to drop the rank. If you just change the, if you are not allowed to make the zeros non-zeros, but you are allowed to make the non-zeros into zeros, it will stay high rank.
So
it's, yeah.
How close are these zeros to sort of being randomly distributed?
Yeah, I mean, they definitely have some, or the ones rather. So if you pick, yeah. So if you picked root n ones in every row at random, it will have this property. So in this sense, it's, yeah.
This is called the birthday paradox. What you just told you is called the birthday paradox. Birthday paradox.
Oh, okay. Oh.
Okay, so it is, there are connections I'm not telling you because I'm just trying to give you lots of examples. Let me move to things that are more related to the heart of this conference. And I want to talk about tensor rank and actually talk about two things related to tensor rank.
We can ask one thing.
Yeah, sure.
All the problems that you suggest, it's hard to find explicit examples of. They all seem to involve some kind of like L infinity bound or some kind of Hamming bound. I mean, you don't measure things in a nicer bound.
Well, in the I mentioned the approximate rank is in. Oh, you mean that it's L infinity, but there it doesn't matter. You could do L2. You could do there you could use L2 and you could get similar. Yeah, but what I in fact, you're right in that what makes the problems hard is that you don't have control over the magnitude. In this approximate rank, you did have because it's a relatively nice norm, but usually changes are arbitrary, and that's what makes the problem hard. But that's what makes it applicable to. Yeah. So I want to talk about tensor rank and motivated, but of course, tensor rank doesn't need any motivation. Some of you are working on proving lower bounds for tensor rank, and it's well motivated in itself. But I want to give extra motivation, some new connections. And in particular, connections to algebraic complexity theory. These are, proving lower bounds for tensors is part of algebraic complexity projects, but it turns out that sometimes they give you more than you think, tensor rank lower bounds. So let me just, to make sure we are on the same page. So here we have, so what's a tensor? So a tensor, we have sets xi of size n. These are the sets of coordinates of the tensor. And this is just a map from the d-dimensional tensor. It's just a d-dimensional matrix like this, full of entries with f, right? That's a tensor. Rank 1 tensor is, so rank of t is 1 if t is simply the tensor power of some vectors, v1 and the rank, in general, the rank of t is minimum r, such that we can write t as t1 plus tr, where all these guys have rank 1. Okay, so that's the tensor rank problem, and we want to find explicit tensors with high rank. We know, again, what do we know? That most t, for most t, we know that the rank of t is what? What's the lower bound for random? It's not n to the d. Yeah, okay, so the best we know is something like n, so it's n to the d, not the best we know, yeah. N to the d minus 1 over d. That's the best we know. We don't really know the answer. Maybe it cannot be more than n to the d minus 1. That's a trivial upper bound of. We don't quite know whether this is needed or not. We don't know asymptotics here. This is a very interesting question, combinatorial question in itself. But anyway, we cannot approach it at all by explicit tensors.
We have a bound that it's very close to that.
For explicit matrices.
No, not for explicit.
No, I know, yeah. So and yeah, I know. But what I want is
basically know that.
You know the upper bounds for any d or for 3?
For any d.
Oh, okay.
For d equals 3, we know everything.
Yeah. For For any d, the upper bound is also of this type. And you know the concept. So this I have to find out from you. Good. Of course, what I'm interested in is explicit, and the best we know is the trivial bound. Just n to the d over 2. How do you get a lower bound like this? Well, you flatten it, right? I mean, you just take an n to the d over 2 by n to the d over 2 matrix, which is identity, and then you make a tensor out of it. So flattening is the only way, and I'll get to flattening more in a second. Flattening is the only way it seems that we have, the only tool, or variety of flattenings is the only tool we have to prove explicit tensor rank lower bound, and that's, of course, a big challenge.
So does the constant matter for you in this explicit?
No, in the explicit, no. In the for what we are, so what's the what's the most basic open problem? So that's what we know, and what we want is explicit t with a rank of t, well, bigger than this. Anything bigger would be fine. So, for example, for d equals 3, it
would twice that or 10 times that?
No, it's a usual question. It seems we would want bigger than that. We would want plus epsilon. So let's say for d equals 3, I would like n to the 1 plus epsilon. But if you give me 100n, I'm sure you'll need to generate some interesting ideas. So both are.
I was thinking we're like 2 or 3.
Yeah, but 2 or 3 maybe next year you can do. I trust you. But
is current technology.
Yeah, no, 2 I know. Yeah, sure. Yeah. So so it seems to me that when we go to the real problem, it seems that it's the same with circle.
Flattening, I didn't understand. What's the flattening?
The flattening is like this. So suppose I want to prove to you, I want to give you an explicit tensor for d equals 4. An explicit tensor, d equals 4, where rank of t is n squared. Right? This is just the same for it. I just take the n squared by n squared identity matrix. Right? And now I call the entries here ij, between 1 and n. I call them here kl. And I make a 4 tensor out of it. Really? Okay. Okay, so we'll get to flattening in a second. I just want to tell you about, some of you may not know this result of Ran-Raz.
If you flatten a rank 1 tensor, it remains rank 1?
Yeah, exactly. That's the point. Because you can put parentheses here. That's the reason. The result of Ran-Raz says that, so proving tensor lower bounds is probably the easiest problem in arithmetic complexity theory. So what are you proving? You're proving circuit lower bounds on arithmetic, on polynomials, on homogeneous polynomials, and you're proving them for the simplest type of circuit that's non-trivial. What's a circuit? It's a depth-3 circuit. What's this decomposition? This decomposition is a sum of product of linear forms, right? That's what it means. Sum of rank 1 tensors is a sum of product of linear forms. So it's a very simple circuit you are proving lower bounds for. But what Ran showed is that this would suffice to prove permanent lower bounds for general arithmetic formulas. So if you can prove, 4, I guess, d less than log n, if you can prove, if you have any explicit tensor, tensor t, where the rank of t is close to what you expect, n to the, let's say, 1 minus little o 1 times d, still weaker than the maximum, but this will imply, so there are other ways to prove permanent lower bounds. Permanent has no polysize arithmetic formulas of any depth. So you're proving a lower bound for depth 3, and that implies a super polynomial lower bound for any.
You
you need it for d, which is growing as a function of n, or can you get it for d equal to 3?
You need it.
Yeah, this is
No, d needs to go. D needs to go super constant d. Yeah, any super constant d would. D is the dimension of the tensor. It's a tensor. It lives in. Yeah.
Okay, so the little of 1 is a function of d. So it's like if it were d minus square root of d.
Yeah, it would be good. Yeah, yeah. The little one is the function of d. So it has to be asymptotic in d. Yeah. Thanks. I want to go back to the flattening. What do I have? 10 minutes. Okay, good. 5 minutes for each topic. Well, there's some discussion time, so it's okay. So like I said, maybe I hope it's clear what this flattening is. In fact, let me give a name to what I just erased there. If I have, I'll just restrict myself now to 4-dimensional tensors. Four-dimensional tensors. So it has, so it's we just have T, I, J, K. And I want to flatten it in 2 different ways into a matrix. And that's, again, this is a trick that, I guess many of you guys use all the time to prove lower bounds on tensors. So I will call T 1, 2, 3, 4 when I take the first 2 coordinates and put them in the rows of a matrix, and the other 2 is, so I make it like this. I put Ij here and Kl here. And I also look at the T of 2, 3, 4, 1. So I put here J, K. So in this number, and here I put L, I. Okay, so there are 2 ways of getting a matrix from a tensor. These are the 2 ways I care about. Okay. And now let me define a new notion of rank for a tensor. You may, just bear with me because there is a reason for this. So here's a weird notion of rank. I don't know how to twiddle. I want to say that it's R, or it's less than R, if I can write T as T1 plus T2 plus TR, but now I don't want this to have rank 1 as tensors. All I want is that either, let me put this in the either the rank of Ti for every I. So for every I, either the rank of Ti when I flatten it this way is 1, or the rank of Ti when I flatten it the other way is 1. Okay, the definition.
Can you explain where the parentheses go in the statement? Is it for all I, one of the things happens, or either one happens?
No. For each one, a different one may happen. Another way to write it.
You only take those 2 and don't take 1, 3, 2.
Because that's all I need. I'll tell you for what. You can. No, wait. There's a.
Okay.
Yeah, you can take. It's very interesting to take other flattenings, but I don't want to. But to your question, another way to write this is to say that T can be written as T prime plus T double prime, and the rank of T prime when I flatten it this way is less than R, and the rank of T double prime when I flatten it the other way, well, up to a factor of 2 maybe, or 1. Okay, so some are allowed to flip this way, some are allowed to flip the other way. Now, why on earth would I define this? So what's the problem, first of all? The problem, it's easy to see that the way I defined it, this twiddle rank cannot be bigger than n squared. Right? It cannot be bigger, and I want a lower bound. I want an explicit tensor. Maybe I should write it here. I would like an explicit tensor an explicit T which has rank, twiddle rank of T is bigger than n to the 1 possible. And why do I want that? It turns out that this will prove lower bounds on the permanent. There's a theorem that we proved with Hrubesch and Yehudayev. That this thing implies that permanent requires, so now I'm moving without defining it precisely to the non-commutative setting where we can, talk about arithmetic circuits computing with non-commuting variables. There is a notion of the permanent with non-commuting variables. Requires exponential size, non-commutative arithmetic circuit. So if you want to prove this as open as a commutative case, it's an easier problem than a commutative case, and I highly recommend working on it first because it's easier to prove lower bounds for non-commutative circuits. This very simple question about this flattening of, and just these two flattenings of rank of tensor rank will give you an exponential lower bound. So that's a challenge. And, okay, questions about this? Actually, that's a good question. So let me tell you what tensor I think you should prove it for. So here's a tensor, an explicit tensor. You can call it the identity tensor. It's a particular T, that's T naught. IJKL is simply 1 if IJ equals KL, okay, and 0 otherwise. Turns out that the flattening of this itself, so here if you flatten it, 1, 2, 3, 4, this gives you the identity. But it's also true if you flatten it the other way. Okay. Because, this means that JK is the same as Li. So, this is my candidate, and actually, so I believe that this lower bound holds for this T naught.
Oh, I see.
Yeah, we have no idea. This is related to the sum of squares problem, not the sum of squares from convex programming, but the sum of squares from algebra. And so, yeah, we don't know this. We worked very hard on this, and there are classical problems related to this that I'm not going to get into the sum of squares, and it's. Let me finish with one last question. So
I'm a little confused.
Yeah.
What are you missing for the proof?
I don't know that this. You remember, this is just the flattening of the tensor itself. What I'm asking is about decomposing it to two tensors, which, a lower bound here means that no matter how you cut it out to two, so write it as a sum of two tensors, at least one of them will have high rank. This is the tensor itself. If you don't split it, yeah.
So have the equations for this notion of rank been studied? So in the usual rank, there's a big study of equations.
No, I think it's pretty complicated. And
it's got this quantifier, either or,
Yeah, it's reducible. It's a reducible. It's still very interesting.
Yeah.
But this.
So anyway, I think it's a very, very simple, concrete question about tensors, which you think should be easy. It implies this something that we've been after for a long time and cannot do, the non-commutative permanent lower bound. But anyway, but there are various partial results, but I'm not going to talk about them. Let me just tell you the last thing, because this is the most connected to this workshop, so I want to get to it. It's about non-commutative rank. Since we got to non-commutative. So if I draw this matrix for you, 0, what's the rank of this matrix? These are variables. 2. Yeah, the rank is 2. So the rank is 2, or this is 2, if x, y commute. They are in what we call, in the usual algebra of polynomials. But the same matrix has rank 3 if they don't commute. They belong to this algebra, where xy is different than yx. Okay, so we can define rank. In fact, I'm just going to define full rank for matrices like this. So what matrix is this? We've seen it in several talks. This is a linear pencil, right? This matrix of matrix whose entries are linear forms in variables. Okay, so I'm going to consider only such matrices. So my matrix A will be x1 z1 plus x2 z2 plus Cn, and each of one of these zi's is just a constant matrix. Okay, but I want to think of these variables as non-commuting variables. So I'm working in the ring. And the question, okay, the definition is a matrix like this has full rank if it cannot be written as a product of, narrower matrices over the ring. So over this ring. So A is called full. This is the formal name. It's called full if and only if there do not exist matrices BC with entries here, such that, and this is n by r, and this is r by n, r less than n, such that A equals BC. So you cannot factor A using matrices, narrower matrices. Then it's full. It's sort of the analog of full rank. Okay, so how? I give you now a matrix A. How difficult it is to tell whether it's full or not. I just give you the matrices Zi.
But do you really want n Zi's and Zi's?
Yeah, it's without loss of generality. You can have two parameters. The size of the matrix and number of variables can differ, but without loss of generality, it's the same number. So it's a complexity problem. I give you something like this. You want to know. So it's just given A is A full. And this turns out to be a really interesting problem for several reasons. First of all, turns out to be the worst problem for the non-commutative skew-symmetric fields. I mean, it captures the question of whether an element in the localization of this algebra is a zero element or not. Turns out to, for those for whom it means anything. But another way to think about it is that it captures the polynomial identity testing when you work with non-commutative polynomials, but you allow division. Allowing division in the non-commutative setting is something extremely complicated. So anyway, it's a very natural problem, extending the kind of problems we look at in algebraic complexity theory. But the third reason, which is connected to invariant theory, is that if you consider when a matrix like this is full, you realize that this property is preserved if you pre and post multiply all the matrices Zi's by a fixed matrix. Right? So Z1 up to Zn, I mean, this linear pencil defined by them is full, if and only if, let's call it, I don't know, M and N, MZ1. I don't change anything if I pre and post multiply by non-singular, So what does it mean? It means that there is an action here. There is an action of GLN post GLN on these tuples, which we talked about, right? But this is not the adjoint action. It's, you don't conjugate the matrices. You look from the left and from the right by different matrices. Another action, what are the invariants? Turns out that the invariants would give you an algorithm to do this. And the invariants were figured out both by Dirksen and I guess Wayman, and also by Domokos and Zubkov, I guess. This corresponds to the quiver that looks like this n times, right? For those who like quivers and arrows. So they figured it out for all quivers, but just for this, what are the invariants? Well, the invariants, here are obvious invariants. Now you should think of these as matrices of variables. The invariants are simply determinants of sums of, what name do I use? BI, Tensor, ZI, or the BIs are all from some. So that we understand all invariants, and now the only question is, well, we know this is an infinite set of invariants because we are allowing all k. The question is, what's the smallest k for which, we know that there's a finite set of invariants there, so it means that, there's a maximum k for which you need to go in order to tell whether a matrix is full or not. What's the largest k? So what's the minimum? What's the degree of generating invariants here? And if this number was polynomial, like it is, for example, for the adjoint action, right? Rasmislov proof gives you an n-squared upper bound on the degree. If this was polynomial, then we could use, we would have a randomized algorithm for this word problem. The best upper bound on this k, as far as I know, is due to Dirksen, is an exponential in it. So.
But is polynomial expected?
I asked some of the experts, and they feel that this is, like Schofield thinks that this should be polynomial.
But for example, you could have polynomial so that the thing is integral over it instead of.
It's yeah. So no, it would be good enough.
Just integral.
Yeah. I think it would be good enough for this algorithm. It will give a polynomial time probabilistic algorithm for PIT for this non-commutative setting.
Integrality is a good thing.
Yeah, absolutely. Yeah, and I think you were interested in the same problem for different.
This occurs on the orbit closure of the liter.
Absolutely, I know. Yeah, so that's why I want to get to it. But let me stop. So.
Thank you very much. Over time, maybe a few short questions.
Yeah, there were many questions in the middle.
It was just an accumulation of questions. Thank you.
Sorry, how are you doing?
Do you think there's
No.
Georgia, he's asking very simple to write.